Hey everyone, so today I got one of my college friends. I'm gonna be putting him through a meta style interview where I'm gonna be asking him two medium to hard level questions in the span of 45 minutes and have him solve those questions. Yeah, pretty much, yeah, around 20 minutes each question. If you don't get to the solution, we're just gonna move on to the next one. And yeah, let's get to the optimal solution. How's that sound?
Yeah, that sounds good with me. 20 minutes a
Okay, cool.
question, meta
Sounds
style.
good. And I'll like provide feedback on everything as well. We're gonna start off with
Okay.
a medium question. Um, Feel free to start reading it. I'll mention it actually. Okay, so we're gonna be given an array, right? An array has some empty spaces, some are zero. Pretty much the empty spaces are zeros, and the other ones are ones, right? Ones basically we have walls and spaces, and basically we start with a ball in a random area in the matrix, and we could start rolling that ball left, up, down, left, or right. But when you start rolling it, it will keep rolling until it hit a wall, right? So basically, what we want to do is if we're given a start and a destination, find out the shortest way that we can get to the destination. If we can't get to the destination, return a one, right? Does that make sense? And feel
Yeah,
free to clarify.
yeah, let me just give it a read. So, there's a ball in a maze with empty spaces, and walls represented as one, and it could go up, down, left, or right, and it won't stop rolling until hitting a wall. When the ball stops, it could choose the next direction. Given an m by n maze, the ball start position and the destination where start is equal to start row and start column and destination. Let me copy this out. Return the shortest distance for the ball to stop at the destination. If the ball cannot stop at destination, return -1. The distance is the number of empty spaces traveled by the ball from the start position excluded to the destination included. Okay, and you may assume that the borders of the maze are all walls. See examples. Um, so to clarify, I guess the input is going to be maze. Is it going to be a 2D matrix? Is that right? With ones and zeros?
2D matrix, yep, ones and zeros.
Okay, so it could be like borders. Okay, so let's see. Let's make up an example here. So if we have actually, let's just make it all empty. If it's all empty, then it's if we have start is equal to 0, 0, end is equal to 2, 2. So in this case, an example path might be, let's say, since we're starting here, 2, 3, 4, 4, right? Because one would be exclusive and then inclusive of the last element. Is that right?
Inclusive of
This
the
would be
last element.
yeah, the destination inclusive.
Okay. If everything's a zero here, though, right?
Yeah. Oh, I see what you mean. Oh, so the actual path would be, sorry, be this because you can't. Yeah. So it'd go down, hit the wall, and then go to the right to get to the destination. So it'd be 4. Is that correct?
Yep. It traveled one, two, three. Yeah, it traveled four.
Okay. Um, and then I guess you could only change directions when you hit a wall. So we're only allowed to change the direction when we hit the wall. And then when the ball stops, you could choose the next direction. Let me see. And then walls are. And then to clarify, can we assume that the start and destination aren't like within a wall, like it's like a valid
Yep.
configuration?
You could assume it's valid. And you could assume that it doesn't start at the destination.
Okay. So listing out the assumptions here. Is there anything else that I should? And I guess we could also assume that start and are in the grid. Like for example, start row and start column is less than uh, the m by n maze size. Is that a
Yep.
valid assumption? Okay.
That you're just trying to clarify if they're actually the start and destination are within the array.
Yeah, exactly. Like for example, if for this maze, like we're not going to get like a start of 100, 100,
Yep.
or a destination of yeah. Okay. Cool. And I guess all elements are either 0 or 1. Is that right?
All
In the
elements are.
matrix?
Yeah.
Okay, sounds good. Um, so I guess I think this makes sense. So I think the brute force solution here would be basically doing a breadth first search from for every possible direction slash every possible direction slash position within the matrix. So, for example, here, let's take this maze and paste it in here. I'll do change it back to 0. So, in this maze, we're able to, since we're at the starting position, we're able to go either up, left, or up, down, left, or right. If we go left, it's basically going to bounce back, and then you could go to the right, but you could go to the right directly anyways. So there's no point in doing that. So let's say mark it with let's say A for like the first move. So A, and then we get to like another. We hit a wall, so we're basically allowed to change directions. So in this case, since it's pretty simple, we'll just go down. But in the breadth first search, we'll just check every single direction plus um, every single direction plus every single let's see every single direction plus position. So if we're going to go down uh, in this position, we'll traverse all of them, but let's say we go left, we'll basically get back to the same position, and then all the other directions will have already been traversed in like the breadth first search. So we'll stop the exploration there, uh, but we'll also traverse downwards where we'll go like A, and then we'll get to the destination. So that'll be like one possible solution. So like this is like 4. But because we're doing a breadth first search, we still need to see what other paths are available, uh, or the other paths are also going to be explored, I should say. So another one would be like B, 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 and then we'll same get here. So that's like one possible solution with breadth first search. If we're trying to find the, let me see, the if we're trying to find like the shortest path, I could see like this is an easy example because there's no walls, but maybe we could use Dijkstra's where you would add, let me see, you would add the like you'd basically be traversing the minimum current path with based on the based on like where the ball is able to roll to. So if we start at start, could check any direction. We go all the way to the right. We'd all go all the way to the right, and then that would be like 1, 2. It'd be 2. We'd go all the way to the bottom, which would be 2 as well.
Wait, are you
So
writing
that would just
anything on? Like it's not.
no, 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 no.
Okay.
I'm just highlighting them in the maze. Um, so I'm thinking, yeah, I'll note this down. So, or BFS, the direction slash position. And then also the current one is extras for basically popping uh, the minimum current path, and if it gets to basically a cycle, by cycle I mean so if you get to a cycle, then cycle meaning you've been in that same direction. Don't continue. Don't continue. Otherwise, if you reach, let's see the destination.
So what are you storing in this priority queue if you're using Dijkstra's?
So the distance, so current, so it'd be like distance, row, column, direction. So, so I actually don't think you need to store. Do we need to store the direction? I don't think we actually need to store the direction because if we only stored in the queue. So we store the distance, the row and column, and then We don't need store direction if we
Okay,
only, yeah,
we have about like less than 10 on this, so let's just code it up. I think you're getting
sure,
to the right kind of
yeah,
approach.
sure. Let me see. So it's a ball with a maze. See shortest. And then so I guess shortest maze or shortest distance maze, which is a list of integers. Yeah, and then we have, what else do we have? Start, which is a list of integers. Destination, integers, and then we'll return any integers. So yeah, we'll return -1. So, well, let's see. So we start at the maze of 0. Okay, let's see. So, and then we'll initialize it to start at 0, start 1, 0. So we'll go, let me see, do we need to keep track of visited? Yeah, we'll keep track of visited. Set, so while q, if, so we'll dist row call pop q q
Cook. Got 5 more minutes.
if 5 more minutes, okay. Equal to column, return dist. Okay, so if this row is equal to in visited, continue visited dot add dist, or it's row call actually. So now we'll go, so now we're in a position where we're able to pivot essentially, like go in each direction. So we'll try that. So if we assume that we're able to pivot into a different direction, we'll go up, down, left, right. So up, down, left, right. So if
I know you mentioned this before, but what's it called? It should be able to roll until it hits a wall.
yeah, yeah. So we'll go, can pivot into a different direction. So we'll go up. So while, let's see, do we need to save temporary parameters? So new while maze row, so while row or new row, let me see, while new row is greater than or equal to 0, and maze new row call, let's see, new row column -1. So if we go up once, and then we basically need to continue until it's gets out of bounds. So while new rows greater than or equal to 0, and maze call equals to 0, we'll go new row minus equal to 1. And then we just need to go up. So this will go in until it either reaches 1 or out of bounds. So we'll just increment it once here. And then if new row not equal to row, we'll go heap q dot heap push pq, and we'll go dist plus row minus new row. Or yeah, that's correct. So because row is going to be bigger, and then new row column, because column will remain the same, and then we'll basically just do the same thing for, why is this having a problem? No. Okay, and then we'll basically be doing the same thing for the other ones. So we'll go down.
Yo, chat, you can hear me,
Down
right? How's the audio?
is
How do y'all
row
think he's
plus
doing?
1, while new row is less than or less than, strictly less than length of maze, and maze new row column is equal to 0. We'll increment this one, and then we need to remove one here. So new row not equal to row. We'll go row. New row is going to be bigger, so we'll go new row minus row, new row column. So we'll do left, which is new call is equal to column -1.
Yo, chat, how's my audio? My audio's
While
good?
new column is greater than or equal to 0, and row, this will remain, and then new call will keep going right. New call minus equal to 1, and then new call plus equal to 1. Let's do the same thing. Left call not equal to call. Let's see, distance plus call minus new call, row call. Then do the same thing here. So plus 1, less than of len maze at 0, new call, plus equal to 1, minus equal to 1. New call, let's see, minus row. So this is going to be for changing, or for each of the directions. And I think this should get us the answer that we're looking for. And we could quickly walk through an
Could we
example.
make it more concise a bit?
Let's
It's a bit hard to
see.
follow.
Yeah. Let's see. If we go, uh, let's see. If we go direction is equal to, let's say, can you do that? Yeah, sure. So we go -1, 0. This is not, doesn't have the formatting I'm used to, but let's say -1, 0. So this is like, if it's row, yeah, 1, 0. Say 0, -1, 0, 1. So for, let's say column move, row move, or actually I'll do row column. Row move, column move in direction. We'll go, let me see what conditions we add. We'll do while new row. Let's see, I'll copy this. Yeah. So while new row is greater, new row equals to row plus row move. New call is equal to call plus call move. New row is greater than equal to 0. See, new row plus equal to row move. New call plus equal to call move. So new row is greater than equal to 0. And row is less than length of maze. New row, new call. So this is for the first, for row, then we'll just do the same thing, and new call greater than or equal to 0, and new row less than len of a 0. So while we're,
Oh, okay. We'll switch to another question. Let me
yeah,
grab it.
we'll
But keep
just do
going, keep going.
this.
I'm grabbing it.
Yep. Dist, new row, let's see. If new row not equal to row, or new call not equal to call, we'll go add this, and then we'll add absolute of new row minus row plus absolute value of new call minus call, new row, and then new column, and then that we could erase all this. So
Nice.
just, yeah. So this should get to the solution that we're looking for.
Let's see. Okay. Give me a sec. Cool. I'm gonna post. I'm gonna. We're gonna go to the next question.
Mm-hmm.
Let me. One sec. Trying to find a good one. So I know all the questions you've done.
We'll see.
Okay, we're gonna get into question 2.
Okay.
So
Okay, let me read this.
yeah,
Or
go
do
ahead,
you want to
read
read
it.
the question?
Yeah, we're essentially we're given a binary tree, and we want to figure out the maximum path between two nodes in the tree. So and yeah, a path is pretty much like from one node to the other, and the maximum path doesn't have to go through the root, essentially.
Okay, so let me see. So a path in a binary tree is a sequence of nodes where each pair of adjacent nodes. Okay. Okay. Assumptions. I guess the tree will have negative values because otherwise you'll just return like yeah, I guess the tree can have negative values, is that right?
Yep.
Negative values. It can appear in a sequence at most once. Okay. Let's see. Path does not. I'll just copy this from here. Path does not. Given the root of the binary tree, return the maximum path sum. And does the path need to start at a leaf or can it start at any node?
It could be any node.
Okay. At any node, not the leaf. Okay, so it could start at any node. So let me draw out an example here. So let's say we have 1. So that'd be the root. And then we have left, right. Oops. Right,
Yo, chat. What are we giving him on the last one?
left, right. Then we have, let's say, -1, or let's say -3, 10, negative, or yeah. And then we have, say, -5, or actually let's do -1. So in this case, the maximum, and then can the maximum path be itself, just like one node?
Yep.
Okay. So example 1. So in this case, let's see, what are we returning? Pass sum, so output would be 10 in this case. Is that correct?
Yep.
Okay, and then we'll just write another quick example. So let's say that's like a single, when a single node is the optimal solution. If we say 5, then this would be, output would be 16. Is that right?
Yep.
Okay, and then I guess we'll do one more example to further clarify things. Let's see. Output is, let's say this is 10, or is it distinct?
No. Could be anything.
No. Yeah, it could be anything, yeah. So in this case, this would be 21 because we could only pick like one of these paths, right? Or actually be 25, right?
Yeah.
So 25 because you could go 10, 10 plus 5.
Yeah.
Okay, interesting. Okay.
Yeah. You captured the
So
cases. What are you thinking?
So I'm thinking that so at each node, I guess we're gonna need to do some traversal and then make some decision there. So for example, in this case, what we wanted, uh, so at each node, make some decision. So at node 10, we had pass some, let me see, we need pass some left, pass some. So a node, so can join to pass that to pass the create substitution 3. It might be an
Sorry for
optimal
the
itself.
sirens in the back. I live in the Tenderloin.
2, or actually this is ex1, and then might be some point within the path ex2. Okay, so let's say if we're gonna do this, if this is the case, then we get uh, add the max path for the left and max path for the, or actually the, for the right, and current node val. So conjoin to current node val. This one, check gains some global value. Might be some point within the path. Return the max pass sum. So return the max pass sum, meaning you either return current node val if both left and right are negative. Otherwise,
Okay.
return max
How are you gonna
left.
know the max path to left and right at each node?
That's the last case right here. So at return the max pass sum, meaning you return the current node val if both in left are negative. Otherwise, you could actually just do this. So it's like current dot val plus left dot val, or left, I guess left sum, or current dot val plus right sum. So this is basically saying take whichever one is the greatest. So current dot val, left sum. So this is like if the left subtree plus the current is higher, you use that, or if the right subtree plus the current val is higher, then you use that, which is going to result in the, I guess, the maximum sum. And then, for example, all this could be negative, so that's why when we're traversing it, we actually check like the first node or the current node val, or sorry, that's the itself. So this one right here, check against some global value. Basically, if itself is like a maximal value, then it's just going to set it as itself.
Okay. Let's get to coding then.
Sure. So we could do, what is this called? Max pass sum. Sure, we'll do Def max path sum of I guess what can we just use like the typical definition of like a tree node?
Yeah, exactly.
So we can just do
What would
like
that be?
val, left, right.
Yeah, and we could assume
Is
that we're given the root, and we could assume that the it's a valid binary tree.
okay. Sounds good. So we'll go root of we'll just keep it as that. And then we'll return we see the max pass sum to be an integer. Let's see. So we'll go let's see, what do we need to return? We need to return we need to return the max and then the path. Okay, sure.
Just, yeah, we're just
So we'll
returning
go,
one number, which is the
yeah,
max.
yeah, I know, but I'm just creating traverse node, and this will return two integers. And then so we'll go let's see, one will be return max and also max path minus one, and then so the max will be zero is equal to traverse for the root return, and then we'll go so let's see if not node return zero return zero zero. So the max is zero. If not node return zero, so we'll go left. Let's see L max L path is equal to traverse node dot left R max R path is equal to traverse node dot right. So what information do we have now and what do we need to return? So let's go through each of these cases. So it can join two paths by creating an optimal solution. So it could either be like if it's joining, it could be like
For time, we only have a few minutes left.
okay. So we'll do this, or this. Okay. So we'll do right, left, right. So we'll do so max join path is let me see max. I think this should be simplified, but for now I'll just do it this way. Node dot val. Node dot val. Actually, I'll do Node dot val plus L path plus R path, and then we'll do node dot val plus L path node dot val plus R path. So this is for the first case. It might be an optimal example. So yeah, we'll also just do this. no dot val, and then might be some point within the path. Let's see, do we catch this? So this is the max that in the current path. And then we just need to do if it's the max itself. Okay, so we'll go max current dot val. Let's see. Actually, we just need to do this max because. So one other way to do this is either set it as a global variable or an instance variable, so that we just don't need to return two values. But just for the sake of this, we'll just return two values instead. And then we'll go max cur dot or node dot val, node dot val, l path, node dot val, r path. So this should get the, basically what this is doing is getting the maximum sum of either itself or with one of the branches, so that when the parent basically tries to use it, it's going to actually get a path instead of getting uh like it won't be a tree, it'll rather just be a path or like basically linked lists there.
I see. Okay, can you walk me through it?
Yeah. So let's say we start at the example. Let's just run one of these examples. So let's say we start at root one. We're gonna, if not node, return its valid value. So we'll go left path. So traverse node dot left. So we'll go -3. -3. Let's see, -3, and then we'll go left. So left is 0, 0, right is 0, 0. So max join path is going to be 0 in this case because it's a negative value. So no dot val plus, I guess one case that this would break for is if everything, let me see, if every node in the tree is negative, because I guess what this is basically saying is that you could pick nothing, but let's see in the question if we need to pick something.
You gotta pick something.
Okay, if we need to pick something, if we need to pick something, if we need to pick something, let me see how we would change this. So if we need to pick something, we basically do max join path is equal to node dot val. And then we go if node dot left if node dot left max, let's see, path, let's see, max path is equal to, let's just say this, sure. If no dot left, this, erase this. So yeah, we'll erase that. And we'll go no dot val, max path is equal to no dot, if no dot left, val path, max, set max join path is equal to max, max join path. Oh, that's annoying.
Okay, you're basically trying to catch the
Yeah,
like.
yeah,
Don't traverse into nuns. Don't
yeah,
traverse into
exactly.
nuns.
Yep.
Okay. All right. We had we're.
Okay.
I
Yeah.
think you're good, heading to the right solution. So, but we
Mhm.
have to. We're gonna move on to the next one. How do you
Sounds
think you
good.
did?
Me?
Yeah.
If I was rating this candidate,
Yeah.
probably let me see. Let's see the previous solution. Mm,
What are you giving them? What's the rating out of strong no, no, yes, or strong yes?
probably leaning no, border. Yeah, probably leaning no.
Leaning no.
That's tricky to say because I guess let me just think. If I was an interviewer, like what my thought process would be here is let me see. Let me think if so for the shortest distance, I guess I would need to know what the optimal solution is. If it's extras and they're on the right track for that, um, then that's a positive signal. But if there's like obviously if they miss the optimal solution, but dextrose still is a valid solution,
Hmm.
then um, that might be like a weak higher or leaning no. And then for the second question, just ran out of time, but on the right track. So that's why it's like probably leaning no. But since the direction was good, and then also the I guess this would be up to you to say like whether it's good or not. Like walking through the examples, stating
Yeah.
assumptions, going through the dry run was okay. So it'd probably end up resulting in it needs more signal or re-interview or depend on other interview results.
I see. Okay. I think I would actually give you a lean higher
Hmm.
because I basically gave you two hard questions. I mean, everyone in the chat said the first one is kind of a hard medium.
Hmm.
So I would, yeah, and then the other one is just straight up hard, but it's easier hard. So, given the circumstance of two hards, and you're able to make good progress with minimal hints, yeah, I'll give it a lean higher or just a higher. But I think where you could have improved was probably like the first one would be the explanation could have been faster and more concise. Like I was
Hmm.
getting lost a bit. I think you were explaining it for like 20 minutes and then coded it
Hmm.
up within 5. I mean, it's a good
Right.
ratio, but yeah, it was like a long-winded explanation. Because I
Hmm.
think at some point you could have just like, yeah, it could have been more
Coded it up.
concise kind of thing.
Yeah, yeah.
And then you mentioned Dijkstra's, but not explained exactly why Dijkstra's would work and not just a regular BFS.
Right, right. I guess the yeah, that's true.
But yeah, I think overall clarified everything really well and talked through the solution. People really liked the way you clarified and talked through the solution. But it was just, yeah, I think it would just be more about pacing. Like in the meta interview, you have 40 minutes to solve both these questions. You would have ran
Right,
out of
right.
time essentially.
Yeah. Are these both tagged for net meta?
Yeah, they'll ask you this.
I see, I see.
So it's more just about getting faster at it. I mean, I don't know if they'll ask you two hard questions. I think they'll ask one easier and one harder. So that's
Yeah,
why
because
I
if
like
this
to
is
give you
both
more.
in 40 minutes, that'd be tough to
Yeah,
do.
I agree. I agree.
But yeah, definitely see what you're saying though.
Yeah. Okay. Overall, good job, man. Catch you later. I'm gonna
Thanks,
grab the
man.
next
All right, I'll
person.
catch you later.
All right. See ya.
All right, see ya.